Now, after understanding the qualitative aspects of the electrolysis and the electrolytic cell, now let us move to the quantitative aspect of the electrolytic cells and the electrolysis. See, we often have been studying that the electrolysis is used in the refining of the impure metals. It is used in the extraction of the metals, and specifically we use them for the very reactive metals. And we know that once the electrolysis is done, the products are formed at the cathode and the anode, and this is how we are able to get the non-metals as well as metals. Now, the more common examples are the electrolysis of alumina, the Hall's process, the refining of the copper by using copper sulfate, like this. So we know it is used in the many different ways and for obtaining the different elements at the cathode and the anode. The most important thing is, once we know the qualitative aspect, is that how much of a substance will be formed at the cathode and how much will be formed at the anode. And the quantity by how much of it is formed depends on what factors. So this all includes, actually is included in this quantitative aspect of the electrolysis, and it was first studied by Michael Faraday. So he gave his two laws in order to explain the quantitative aspect of the electrolysis, which are called Faraday's laws of electrolysis. Now, his first law states that the amount of substance deposited at any electrode is directly proportional to the amount of charge passed through the electrode. So the amount of substance deposited at any electrode is directly proportional to the amount of the charge passed through the electrode. It is the charge which is going to decide that how much of the substance will be deposited. Now we can convert this into formula, which can be written as this M will be proportional to Q, where your M is amount of substance deposited and Q is the charge passed. But we know Q is always equal to IT, where this I is current and T is time in seconds. Always Q is equal to IT, we know this. So we can write this formula as M proportional to IT, and this proportionality is opened by a constant called Z, and this Z is called electrochemical equivalent of a substance. So this is what is the formula is. So the amount of the substance deposited, basically the proportionality constant involved is called electrochemical equivalent, ECE, of the substance. Every substance has its own ECE. Now let us first understand what is this Z or ECE is. This ECE, the electrochemical equivalent, is actually equal to the equivalent mass of substance upon 96500, which is 1 Faraday's, the charge present on 1 mole of electrons. So this is 1 Faraday. We can define Z as the mass of substance deposited by 1 Faraday by 1 Faraday. We are dividing it by 1 Faraday. It should not be called 1 Faraday, actually by 1 coulomb of charge. So, see, equivalent mass we know is the mass which of a substance which is deposited by 1 Faraday. Whereas the electrochemical equivalent is the amount of the substance which gets deposited by 1 coulomb of charge. That is why we are dividing it by 1 Faraday 96500. And now let us move further. Once we know this Z, that what is an equivalent mass exactly is, we know it is equivalent mass is molar mass upon n factor. What is n factor is the number of electrons exchanged or accepted or lost by a species during a reaction. For acids, it is the basicity, the number of replaceable H plus ions. For bases, it is the acidity, the number of replaceable OH minus ions, and this is how we can find out the N. So we can write the Z as molar mass upon N into 96500. So the formula which we can get can be written as molar mass upon N 96500 into I and into T. So this is how we can find out the amount of substance deposited during the electrolysis at particular electrode, which depends upon this much of charge passed multiplied by the substance deposited by 1 unit charge, which is 1 coulombs. So we are simply multiplying it by how many coulombs of the charge which is passed through it. So that is how it becomes very clear. Before moving further, let me explain it to you, this Faraday's and the Z, much more clearly. See, let me first describe you what is 1 Faraday's. It is charge present on 1 mole of electrons. So charge on 1 electron we know is 1.6 into 10 to the power minus 19 coulombs, and the number of particles in 1 mole will be 6.02 to 10 to the power 23. When we multiply this, we get 965,400 coulombs. The answer is 96480 something, which is actually rounded off to 96500 coulombs. So the charge present on 1 mole of electrons is 96500 coulombs, so which is called 1 Faraday. Now see here, we can easily make out from here, you can understand this, like if we have 1 mole of sodium, 1 mole of magnesium and 1 mole of aluminium, we know if we want to deposit them, we will use 1 electron here, 1 mole of electron. For this we will use 2 moles of electron to deposit whole of the 1 mole of magnesium, and we will be using 3 moles of electron to deposit completely 1 mole of aluminium. Now we must understand 1 mole of sodium is 23 and divided by the 1 mole of electron used. So this equivalent mass will be 23. Here in this case, we know that 1 mole of this needs 2 moles of electrons. 2. So n factor in this case is 2. So the amount of, what is equivalent mass? I told you, it is the amount of the substance deposited by 1 Faraday, 1 mole of electrons. So 2 Faraday is depositing 1 mole, 24 grams, so 1 Faraday will deposit by 2, that means 12. 27 is aluminium, 1 mole of aluminium, and it is deposited by 3 moles of electron, 3 Faradays, so 27 by 3 will make it 9. So this 23, 12 and 9 are the equivalent mass, but they are not the Z's. These are the amount of the substances deposited by 1 Faraday. But the amount of the substance deposited by, again, if represented in the form of deposited by 1 Coulomb, that will be called as Z. So we can make out that 96500, this 23 we can write as 96500 coulombs are depositing 23 grams. So 1 coulomb will deposit 23 upon 96500, which is called the Z for magnesium. Similarly, we will say 96500 coulombs of charge is depositing 12 grams of, sorry, this was for sodium. So here in the case of magnesium, we will say 96500 coulombs of the charge is depositing 12 grams of magnesium. So the 1 coulomb will deposit 12 upon 96500 of this, of the substance, which will be the Z for magnesium. And similarly, 96500 coulombs of charge is depositing 13 grams of aluminium. So 1 coulomb of this will deposit 13 by 96500. Z for, it will be for aluminium. So this is how we determine Z, and this is what is Faraday's. Now let us move to the second law of the Faraday's. Second law of Faraday's. It states that the amount of substance deposited at any electrode on passing same amount of charge depends on the equivalent mass of the substance. See, amount of substance deposited at any electrode on passing same amount of the charge depends on the equivalent mass of the substance. It's very clear, because we know the M is equivalent mass upon 96500 into Q. See, if the Q passed is same, definitely this will depend on what? Equivalent mass, which is basically, therefore the second law is the other form of the first law, and it is basically used to compare the equivalent masses, the amount of the substance deposited between two different substances or out of two different substances. And it is basically used to find out the valencies, the atomic masses, the equivalent masses of the different substances, which we normally do, we used to do in the first chapter in the earlier syllabus. But since the equivalent masses is not there anymore, or normality we don't have anymore, so that this aspect is only used here in this Faraday's law only. Otherwise, we used to teach, it is actually used to be there in the form of normality. Also, sometimes the molar conductance, which we have done at infinite dilution or molar conductivity, we have another term which is called equivalent conductivity if the normality or equivalent mass is actually concerned in that. But since again the equivalent concept has been completely taken off from the syllabus, we are having this use of this term here only. So this is what is the second law is. It can be explained like if we have two basically electrolytic vessels, both are connected in series. One is having zinc in zinc sulfate, other is having copper in copper sulfate. So I can write is mass of copper deposited. If it is like this, let me write down the formula now. The mass of copper deposited upon mass of zinc deposited will be equal to equivalent mass of Cu2 plus equivalent mass of Zn2 plus, because the Q passed when those two electrolytic cells were connected in the series was same. So this mass deposited was proportional to the equivalent mass, and this is how we know the mass of the one of the species. We can find out the mass of the other substance deposited, and if we know the equivalent mass of the one, we can find out the equivalent mass of the other. So this is how this law can be used in the different ways. Now let us see a numerical that how the Faraday's laws are used. The numerical is the solution of aluminium chloride was electrolyzed for 10 minutes by passing current of 5 amperes. Find the mass of aluminium 27 deposited. So we know that from AlCl3 that the N factor, the charge on the aluminium is 3, so its N is 3. Its mass is, molar mass is 27. Current passed is 5 amperes, and time is 60 seconds into 10 minutes will make it 600 seconds. So we know M is the molar mass upon N into 96500 into I into T. It's 27 by 3, 96500, 5 into 600. The 20 gets cancelled here, it will make it 9. So the answer comes out to be 27.2797 grams. So this is how this much of the aluminium will be deposited on passing 5 amperes of current for time 10 minutes, and this is how we can use the information which was given by the Faradays in finding out the quantitatively how much of the substance is deposited at different electrodes.